you not understand what life is. It's going to totally change your view on life. So before we go any further, I don't remember exactly where we were on this, so I want to take a few minutes, and my first question is the variable c. What is the variable c? Speed of light. Good. So make sure you know that the variable c is speed of light. It has a value. You do have to memorize this value. Okay? I'm telling you now, you do have to know that number. It's 3 times 10 to the 8th meters per second, or what's the easier way to say it? 300 million meters per second. Okay? We've already talked about this funky looking upside down Y. What is the Greek letter? What? This is not a Mexican restaurant. It is lambda. Okay? And what does it stand for? What does it represent? Wavelength. Okay? And wavelength is the distance between two waves. Notes. Okay? This is not a V. It's really a Greek symbol. And again, if you want to rewrite it, again, this is how I kind of write lambda. This is kind of how I write that symbol. What is that symbol? What is that Greek letter? What is this Greek symbol? Nu. Very good. Nu. And it stands for frequency, which is how often a wave passes a given point in a given amount of time. So the first thing is, and I can't believe I didn't do this yesterday. I guess I ran out of time. Is let's draw our handy-dandy triangle. Okay. So in this triangle, where is the variable c going to go? The top. Very good. Okay. The other two are obviously going to be on the bottom. So we've got c equals lambda times nu. Now, we've already established this. That c is, again, what? Speed of light. Will the speed of light ever change? No. So what do we call variables that never change? Constants. Very good. They're constants. So this is 3 times 10 to the 8 meters per second. So my question to you is, will you ever be solving for the variable c? No, you already know what it is. You don't have to solve for it. So the only two things we can use to solve in this particular triangle is either lambda or nu. And if you want to add this in, it's totally up to you. But again, this is lambda, not labda, whatever you said. Okay. And that is nu. All right. So these are the two things that we're going to be solving for, is wavelength and then again frequency. Now, let's see if you remember, after every unit triangle, what do I always draw? Wait a second, I gave the answer. After every triangle, what do I draw? The unit triangle. Alright, so we've got to understand what the units are. Now, the reason I'm doing this one is very specific. This one is a little weird. Okay, we already know that the speed of light is meters per second. Alright, the bottom left is lambda, which again, what does it stand for? Wavelength. And what do we measure distance in a basic? Is a meter, okay? So this is where the units get a little weird. Now, all I want you to do is understand what the unit is, not why it is. Just know it's a fact, not something that you actually have to apply in this case. So mathematically, what are we going to do to these two things? We're going to divide. So I'm going to come over here on this page, and we're going to do meter per second divided by meter. Now, this is not really a great way to do this, so can I rearrange this in a different way? Yep, so I can say meters per second times 1 over meter. Is that saying the exact same thing? Okay, so since we see it in this perspective, it makes it a little bit easier to see. What do you guys notice happens? Meters cancel. However, is it just seconds that are left? Very good. This is what is left. Now, this is not a very good way to write our unit. It's not the most appropriate way. There's another way to write this in mathematical terms. This is a new thing you've probably never seen. So I need you to kind of stick this on your brain, that this is the way to properly write it. That is the unit. Again, I'm not asking you to understand why or how or what that means. Just understand that s to the negative first is the unit. But what does it mean mathematically? It means 1 over s. So anytime from here on out in any of your math career, if you see anything raised to the negative first power, all that means is 1 over that thing, or the reciprocal of. Does that make sense? Okay, so these two things are equal in essence. Okay, but that is the unit. So when I come back over here, this is what I'm going to plug in there. So that is your unit triangle for this. Probably Thursday, we're going to work with this triangle, depending on how far we get today. So this is the triangle that you guys can work with on that. The last thing that I want to talk about is this specific formula. Actually, let me come over here and do it like this. It's a little easier to see it when you write it larger. So lambda nu. If C is a constant, and what do constants mean? They never change. They never stay the same. If my wavelength gets longer, which means it gets farther and farther apart, mathematically, what does frequency have to do in order to maintain this constant? So this number has to get smaller, or vice versa. What happens if my wavelength gets shorter and shorter and shorter? What has to happen to your frequency? Wait, I did that wrong. Sorry. My bad. I did it backwards. If that goes down, then what? This has to go up. So how are frequency and wavelength related? Inversely proportional. So read that purple-pink sign. I would highlight that if I were you. So, or put a star beside it. The wavelength, this one right here, the wavelength is inversely proportional to the frequency. That is a major concept that you guys have to kind of grasp a hold of. So let me show you this from a picture standpoint. We've already seen this. What do you notice about the wavelength as it goes down the page? It gets closer and closer together. And if I clap this, Cody, what happens to my claps as I go down? They get faster. Okay? So, do you agree that this picture also proves that to be true? Okay? So, the shorter the wavelength, the higher the frequency. Okay? Please keep that in mind. All right. So, this is a picture that I want to. It's just a simple kind of question. Which wave up here has the? How do I want to ask this? Shortest wavelength, top or bottom? Bottom. Okay. Which wave up here has the highest frequency? The bottom. Very good. And if you clap that, would you agree you'd clap more times for the bottom? Yep. And that's the kind of the mental concept that you can take from this. All right, this picture right here, there's 2 questions at the bottom. Take just a second and answer those 2 questions. All right, so the first one should be easy. I know most of you are probably still writing the second one. But question A is, which has the longest wavelength is really what it's supposed to say. Which one, A or B? B, okay? So what does that tell us? And this is important. If B has a longer wavelength, what does that tell us about the frequency of A? It's higher or faster, okay? Higher is really the correct terminology. It has a higher frequency. And again, if you clap that out, would you clap more for the topic? Do y'all like the clap things? That help visualize it a little better? Spectacular. Good. And the last one, what is the relationship between wavelength and frequency? Inversely proportional. Or you could say as one goes up, the other goes down. That's another way to kind of phrase that. All right, very good. So let's move on. Here's just another picture. There's in this picture, the reason I left this in here is this picture right here. That part of the picture. So circle that. I know it's kind of dark and it may be hard to see, but the reason I left this in here is what we're fixing to get into in this next topic is energy. And I want you guys to understand how energy is related to waves, okay, and related to the electromagnetic spectrum. You already know this. Is gamma rays, by the way, I know this is, you probably don't know this, but this crooked looking Y is the Greek letter gamma, the lowercase Greek gamma. The lambda is an upside down version of it. That makes sense? Okay, so that's a good point there. So you know this. Are gamma rays or radio waves more dangerous? Gamma rays. So does gamma have more energy or less energy? More energy. Well, that makes complete sense. So if you compare energy to wavelength and energy to frequency, which one is energy directly related to? Frequency. The higher the frequency, the more energy that wave has. And that is exactly related to exactly what we've been talking about. Okay? Yes, sir. Sure. Be a superhero, too. I'm sure there is some device out there that has gamma ray possibilities. That it has enough energy to shoot out a gamma gun. All right, so how did they figure all of this out? What are some of the things they did? So the first thing they did was the photoelectric effect. I'm telling you now, this definition is a test question. Okay, make sure you know this. This is a TQ. All I need you to know is what the photoelectric effect is. Before I even read the definition, you're going to know what it is. Because we're going to take this term, photoelectric effect, and we're going to break it down into something that's a little more understandable. Now, what does the prefix photo mean, like in photosynthesis? Not a picture. Come on now. Light, thank you. Photo means light. Because what is photosynthesis? You use light to synthesize energy. Okay? Now, electric. Now, we know that's electricity. However, what do you have to have? Electrons, thank you. Okay? So here's what the photoelectric effect is. You know what effect means, cause and effect. The photoelectric effect is the effect that light has on what, Cody? Jack? Ralston? Thank you. So let's read this again. The photoelectric effect is the effect that light has on an electron. So what does it do? What does it make? What makes it happen? So photoelectric effect refers to the emission. Let's stop right there and make sure. What does emission mean? That's why I stopped there. Thank you. To give off. Emission means to give off. Refers to the giving off of electrons from a metal when light shines on a metal. Now, again, yesterday I harped on this. Is light something you can always see? No. So does it mean visible light that we can actually like shine a flashlight on it and it work? No, we're not talking about that light. So light here essentially is what we're referring to is we're talking about energy. Because light is a form of energy. Think about X-rays. Are X-rays a form of light? You just can't see them, and it's a form of energy. Question somewhere. I mean, you're thinking of visible light. Again, you got to think about it from a different perspective. Potentially, but it's not going to make it jump off now. Because it doesn't have enough energy. Flashlights don't have enough energy to do that. Okay? Now, which creates an electric current. Now, an electric current is nothing more, and please write this at the bottom, nothing more than a flow of electrons. So if you take enough energy from that light and you slam it into a metal, I mean, it runs into it at the speed of light, which is how much? 300 million meters per second. If there's enough energy in that light, it can knock electrons off of an atom. No, actually, you're right. No, stop. What you just said is exactly right. How many of you have accidentally left tinfoil on something in a microwave? What happens? Stop. Let me think about this. Is aluminum foil a metal? Yes. What's being shot at that piece of aluminum foil? Microwaves, which is a form of light, which is a form of energy. So exactly what you just said is correct. If you want to see something cool, take a CD and put it in there. Watch what happens. Not your mother's, because she may kill you if you do it. But I've got a microwave, but I'm not doing it because it messes it up. Let me turn this on. Hopefully this works. Again, is it a metal? Microwaves. Microwaves. Here it goes. I'm sorry it's so long. Shh. Okay. It will catch on fire if you leave it in there too long. But again, it's one of those things that, no, go back to this. You've got to remember that microwaves are a form of light energy that you just can't see. So that aluminum foil in a microwave is a perfect example of this. Now, light. It's those green wavy looking things, right? So light travels in what form? Travels in waves. Now again, we've already established that light is also a form of energy. And if that light, for the 12th time today, do you have to be able to see this for it to work? No, you don't. If that light has enough energy, it can take this piece of metal and knock electrons off of it. Now, the experiment in the microwave is a little different from this because we're not trapping those electrons, because what happens is that these electrons are knocked off and it is collected by this pole, which is called the anode, and we're not going to get into the depth of that. But what happens is these electrons can run down this wire and create a voltage source. Okay? Not only is that happening, the electrons can actually go back and forth. So they can jump back and forth between this pole and create a different effect. No. It's different, yeah. So, radiant energy. What is radiant energy? That is a fancy term for what? Light. It is a fancy term for light. When you say someone looks radiant, what does that mean? They're glowing. Okay, glowing. So what happens is, again, you get radiant energy that comes in. If it's got enough, it can make an electron jump or knock it off, essentially, and go to the other pole. So this is what it says. When the metal is hooked to an electrode, it is made positive. It pulls the electrons away from the target metal, and they are measured that way while being returned to the target metal. Now, that's kind of confusing, but this is the important part. When there is no circuitry, which basically means there's nothing hooked up to it, and it is just light, and again, what is light a form of? Energy, hitting a target metal, the electrons are ejected, which basically means knocked off. But as the metal grows more positive, it pulls them back. So think about this. If I take this piece of metal and I pull all these negative things off, well, what are you left with? Positives. Exactly. So the more and more positive this thing gets, well, what are the electrons going to want to do? They're going to want to jump back to it, because what do positives and negatives do? They attract. And so that's essentially exactly what's going on here. Okay? Exactly. Now this, down here, this is the AL in the MW. The aluminum in the microwave. So I was shorthanded that. Because, again, what is radiant energy? Light. Okay? But in this case, this is microwave. And then you have all of these things that can be emitted off, and it can knock the electrons off. And in the case of the microwave, you can see it. So here's the crazy part. And this is the visual comprehension that you'll understand now. If we hit something metal with enough energy, such as a microwave, is it possible to see the results of it? What are you seeing? Well, that is true. You're seeing a reaction, but are you seeing light being given back off? Okay, so that's how you know that energy is being exchanged here. So this is where it gets a little deep. There's two key words we're going to talk about. This is the first one you're going to need to know. Quantum. Here's what quantum is. Quantum is energy. Nothing more than that. Quantum is energy. But it's a specific amount of energy. I'm telling you now, this first bullet is a test question. You need to know the definition of what quantum is. Quantum is what again? It's energy. But it's the minimum quantity of energy that can be gained or lost. Let me put it into an understanding that will be really easy for you guys. How many of you like playing paintball? Okay. All right. What makes a paintball a paintball? The paint. Okay. If you don't have paint inside of it, is it a paintball? No. So here's what I need you to imagine. The quantum is like the paint inside of a paintball? Paint. Okay? Well, light has a quantum. But here's the important part. Can you have half of a paintball? Can you shoot half a paintball? No. You can't shoot half a paintball unless it breaks. We're not talking about that. We're talking about literal, yeah. So my objective for you to understand here is that can you gain or lose half of an electron? You can't shoot half of a paintball. So can you gain or lose half of a quantum? You gain it or you lose it. There is no in between. Okay? So in layman's, it is packets of energy that are released or gained up to a certain point. It's an all or nothing. You either gain it or you don't. You either lose it or you don't. God bless you. Okay? So again, it is a paintball. So a paintball is not a paintball without the paint. So again, think about the paint as the quantum. Now, we're going to talk about what the paintball is in just a second. Yes, sir. We're getting there. We're getting there. Okay? Now, so what does all this mean? So just a few minutes ago, we talked about this light hitting a piece of metal and knocking an electron off. So now let's go a little bit more specific. What is making that electron be knocked off? What's that Q word? Quantum. So look, an electron doesn't move without a quantum. And here's where this is going to take us. We're going to talk about Bohr's model in just a minute. And what we're going to learn about Bohr is how he talked about how electrons move. But let's make it very simple for just a sec. Actually, it'll be just after this. No, this is Max Planck. Max Planck. So what Max Planck did is he tried to define how much energy a source of light has, some piece of the electromagnetic spectrum. So the German physicist proposed the following relationship between a quantum of energy and the frequency. So what Max Planck did is he relates energy to frequency. Now we already know the relationship. The more frequency you have, what does that tell you about the energy? The more energy you have. We already know that. But this guy's the reason we know that. Okay, he discovered that fact. And what he did is he applied it to a mathematical relationship. So here's what he said. He said E equals H, and that's not a V. It's that funky Greek letter again. What is it? Nu. So if you want to kind of write this in, this is nu. So you know what E is. You know that's energy. You know what nu is. You know that's frequency. But the H is the new one. What is H? Look at that last bullet. Planck's constant. Now, the good news about that number is you do not have to memorize it. I'm going to give you that number. Okay? The only number you have to memorize in this chapter is the speed of light, which is what again? 300 million. Okay? What was I going to say about that? Oh, let me ask you something. Is that a really big number or a really small number? It's a really freaking small number. How do you know it's really small? It's negative x1. Now, this is another kind of a funky question. Is that number closer to 1 or farther from 1 than Avogadro's number? How do you know it's farther from 1? Very good. The exponent's bigger. So this is to the 34th and Avogadro's to the 23rd. So you know how big Avogadro is, right? This is even smaller than that is big. That just doesn't make logical sense. Okay? Now, so we've got a 3-variable equation. So what do you think we can do with it? What can we do with it? We can put it in a triangle. You guys are learning. Now, looking at the formula, where does the E go? At the top. Very good. Some of you are learning. All right. What's in the bottom left? H. And what is in the bottom right? Not the V. Nu. It's nu. N-U. Nu. All right. So, we already know that H is what's called Planck's what? So what does that mean? It'll never change. And help me out. I'm making sure I write it. It's 6.626, right? Times 10 to the negative 34th joules times seconds. So if that number never, ever, ever changes, are you going to be asked to calculate H? No, you'll never do that. So the only two variables you're going to need in this problem are what two? E and nu, that's it. So I can ask you what is the energy of this wave, or I can ask you what's the frequency of this wave. That's the only two things I can ask you. Okay? And again, how are these two things related? The more the frequency, the higher, the more energy it has. So they're going to be directly related. Now, after every triangle we do what I always do next. Unit. Okay, it's important. And this one's going to be a little weird too. So just stay with me. But it should make sense again. Now, let's go ahead and plug our constant in because we know what our constant is. It's going to be J times S. So that's our Planck constant unit. And you've already learned this. What is the metric unit of energy? Joules. What's the American unit? Think about food. Calories. Very good. Calories. All right. So we've got a missing unit here. So let's see if we can figure out what it is. I'm going to come over to the next page and we'll come back and we'll fill this in just a second. So I have J divided by J times S. What happens? J's cancel, which leaves me with what? Very good. Which is S. Very good. You guys are learning. Look at that. You can learn. Your parents aren't telling the truth sometimes. Okay? S to the negative first. And it's exactly what we did a minute ago. We said the frequency unit is S to the negative first. And for the second time again, I'm not asking you to understand why it's to the negative first or inverse. Just accept it. Yes, sir. That is a great question. And I don't know how to explain it to the degree that it'll be comprehensible. I don't even know how to explain it. Think about the unit. It's joules times seconds. So it's the amount of energy that is received or given off during time. Does that kind of make a little bit more sense? Now, the part that I've never understood is why is it constant? Because my theory is, and again, I know I'm wrong, my theory is if the form of light changes, shouldn't the energy also change with it? Does that make sense? That's the part that I don't get. What my thinking behind it is because just like we talked about it a minute ago, you can only absorb a quantum at a time. So my thinking is that a quantum has that amount of energy. Every quantum does. Like from gamma to X-ray to infrared to radio. The form of energy. I mean, the state of matter will change. It's all in light. To a degree. So who knows where he came up with that? That's beyond my knowledge base. It may be something interesting to look up. Well, guess who showed up and made it really complicated? Who's that guy? That is Einstein. And of course, everything Einstein does is really complicated, but it'll make sense. So what everything Planck did was what I'm going to say it was in human size. Okay, so basically these lights that are coming down, the sunlight that comes through, the X-ray machines that we have, Planck did it with everything that's human size. Einstein comes along and says, guess what? I'm going to turn it to a really, 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 really tiny size called the atom. So what he said is, Planck, I'm going to take your work and I'm going to tweak it, and I'm going to say it also applies to electrons. Now, what's the problem with being able to prove that? You can't see it. It's really tiny. Does that make sense? So it was really hard to be able to say that one single electron acts like that one piece of light that we can physically see. But he proved it, because obviously Einstein was right about a lot of things. So this is what he did. And this is the next word that you guys need to know. A photon. Now, what does photo mean? It's a light. So here is what a photon is in a very simplistic thing. It is a ball of light. or a paintball. It is the shell. So this is where my theory kind of wraps up. We've already established that a paintball can't be a paintball without paint. Well, you can't have a paintball without the shell either. Okay? So in chemistry terms, the photon is that ball, is that shell, and what is the energy inside of it? A quantum. Okay? So this is what Einstein theorized, is this photon, is this ball of light carrying a quantum of energy. And a quantum is always the same amount. Now, can you be hit with a bunch of photons? Sure. Okay? But each photon is going to be the exact same. But here's where it takes a turn for the weirdness. A photon is a particle of electromagnetic radiation having zero mass. And I know what you're thinking, what, how, why, Einstein? But this is still one of the parts of theoretical physics that they have not figured out. What is light? And why does it work the way it works? And I have a foreshadowing. It's only going to get weirder. So just, again, hold on for the ride. We won't get to that till tomorrow. So what it is, it's again, a photon is a particle of zero mass carrying a quantum of energy. So here was the question people said. Well, then is light matter? Because the very first chapter, what is the definition of matter? Has mass and takes up space. Well, Einstein said it doesn't have any mass, but here's the crazy question. Can light fill up a room? Can it? That is a thought question. Is it physically taking up space in a room? But can you stop it from being in a room? It's an interesting question. Okay. But what is darkness? It's the absence of light. So if it can take, if we say that darkness is the absence of it, doesn't mean when it's there it is taking up some sort of space? Is it? It's philosophical to the point that no one can answer that question. And this is why Einstein was a genius, is he mathematically proved all this stuff and no one can answer why it's right and wrong. We don't know. It's going to take someone way smarter than him and me to figure that out. So again, the whole essence in a teenager's brain, which is what you all are, of how do I apply this and how can I remember this, is that a paintball must be filled with paint, just as a photon must be filled with quantum. And all quantum is energy. Okay? All quantum is energy. So the energy of the particular photon depends upon the frequency. So what is the only difference between Einstein's formula and Planck's formula? No. He added the word photon. That's it. That's the only difference. So Planck talked about, again, what I would say is human size, things that we can visibly see. But then Einstein got down on that the atomic level, and he began talking about electrons. Depends on how you define smart. I mean, truthfully, he is. Sir. Okay. True. No. It's not made of electrons. Electrons are affected by light. It's not made up of an electron. Exactly. Light can be affected by gravity. You're exactly right. Okay. And that is the problem with theoretical physics of trying to prove all of this stuff. Why is it affected? And how is it affected? That should be your life's challenge. Make it your goal. What is light? I think you got it. I think you have a mission now. Okay? So, I told you there was, stay with me. I told you there was two keywords. The first one was quantum. You know, quantum's just a form of energy. And again, it's specific. You can either gain it or you lose it. The second word is quantitized. Now, what is a quantity? It's an amount, which is easy. So if I were to ask you to go up some stairs, now let's theoretically pretend that these stairs are perfect, which means that every step is the exact same distance from the next. Okay? If they're perfect, would you agree that it would require the exact same amount of energy for every step? Yes. Just quit. Just quit. You're overthinking. Just quit. So again, if every step is the same height, go early. Okay. Then each step requires the same amount of energy. So here's where this relates. Let's pretend that I took an electron and I put it on that step. What amount of energy would require it to get to the next step? It would require a specific amount, right? Guess what that specific amount is? A quantum. Let me finish this. Let me get to this and I'll go back. So, every time you hit that same electron with a single photon, what's it going to do? It's going to go to the next step. Okay? Because every photon carries the same amount of energy. So the ramp is a continuous change in height. So if you look at it, if you try to walk up this ramp, by the time you got to this point, is it harder or easier than at the bottom? It's much harder because your angle has changed. So is it more energy or less energy? It's more energy. Well, by the time you got to this point in the step, did it require more or less energy than the previous one? The exact same amount. So that is where Bohr comes into play with this, is that he theorized that this is exactly what an atom was like. It was like a set of stairs. And every time that an electron wanted to go up an energy level or come back down, it only required a specific amount of energy. And what was that specific amount? A quantum of energy. Okay. So stairs, quantitized change in height. You can only stop on the stairs, not between them. And so kind of keep that in mind. You can either take in a quantum or you can't. You can either give one off or you don't give one off at all. Okay? How much time we got left? All right, we'll stop here until tomorrow.